everyone, we are from Group 3. Today we'll present pulse modulation and multiplexing. Let's go! Let's start with introduction to pulse modulation. Pulse modulation is a type of modulation in which the signal is transmitted in the form of pulses. It can be used to transmit analog information. In pulse modulation, continuous signals are sampled at regular intervals. These are the three primary types of pulse modulation. First, we have pulse amplitude modulation, PAM, where this technique modifies the amplitude of the carrier pulse signal to encode information. Next, we have pulse width modulation, PWM. In this type, the width of the carrier pulse signal is varied according to the input signal. Last, we have pulse position modulation, PPM. This approach alters the position of the pulse signal in relation to the carrier. Move on to sampling. Sampling is the process of converting a continuous time signal into a discrete time signal by measuring the signal's amplitude at uniform intervals. According to Nyquist sampling theorem, state that for accurate reconstruction of an analog signal, the sampling rate must be at least twice the highest frequency present in the signal. This minimum rate is called Nyquist rate. Then we have type of sampling. We have ideal sampling, natural sampling, and flat top sampling. Quantization is the process of converting the sample amplitudes of a continuous analog signal into discrete level, enabling digital representations. We have two types of quantization. First, we have uniform quantization, where all quantization levels are equally spaced. It is suitable for signals with a uniform amplitude distribution, while for non-uniform quantization, levels are not equally spaced. For smaller intervals are used for low amplitudes and vice versa, commonly implemented using compounding, micro-law, and A-law in PCM systems. Common terms we use in quantization is level, quantization interval, quantization value, and quantization error or noise.
Let's start understanding what bit depth is and why it matters in digital systems. In simple terms, bit depth refers to the number of bits used to represent each sample of a signal. It's a key factor that influences the quality and precision of digital signals. Bit depth defines the resolution of the signal. For example, a 24-bit sampling can store more information than a 16-bit sampling, which means a 24-bit system has higher capacity to capture finer details in the signal, making it more accurate and precise. What is the impact on quality? So, with a high bit depth, the signal dynamic range will increase. This means that the system can represent both very quiet and very loud parts of a signal more accurately, and at the same time it reduces the quantization noise, which is the distortion caused when a continuous signal is converted into digital signal. Sensitivity to noise. However, there's a trade-off. High bit depth are more sensitive to noise and interference, which means we need better error correction techniques and a higher signal to noise ratio or SNR to ensure the signal quality. Now we look into bit depth consideration. Higher bit depth gives us high accuracy, meaning the signal we capture and transmit is closer to the original source. This is important for application like audio recording, video processing, and communication systems. However, higher bit depth comes with challenges. First, we need more complex hardware for encoding, decoding, and processing the signal. This will add the system cost, of course. For example, professional grade equipment used in studios or advanced communication systems is significantly more expensive than consumer grade hardware. Second, it increases power consumption. Since we are processing more data, it requires more computational resources, which lead to higher energy usage. This is particularly important for battery-powered devices like smartphones or hearing aids, where efficiency is critical. Third, it demands higher computational power. System needs to process and store larger volumes of data, which means we need better processor and more memory. Additionally, as bit depth increase, so does the amount of data transmitted. This means we need more bandwidth to handle the increased data. For systems with limited bandwidth, like wireless communication, we must use fully balanced carefully balance the trade-off between bit depth and available bandwidth. If you look at the graph, you can see how the waveform becomes smoother as the bit depth increases. With lower bit depth, the signal appears blocky because it cannot capture all the fine details. But with higher bit depth, the waveform closely matches the original signal.
Okay, now we'll look at the study of what is multiplexing or muxing, which contributes to today's wide range accessibility of telecom tools when transmitting and receiving information at one time. So, for example, the ability to switch through different TV channels through one main cable connection is due to multiplexing. It's devised to transmit multiple information signals, analog or digital, through one high speed communication line over a shared medium. We'd get one traveling composite signal, like in the picture, that goes into a demultiplexer for reprocessing into separate signal lines for different functions. So, we've simplified the system management with increased efficiency by boosting the transmission line capacity while cutting high costs of physical infrastructures. One technique for this is called the frequency division muxing that focuses on analog signal transmissions. The range of frequencies that we call bandwidth in one transmission is divided into smaller independent frequency channels in parallel called carriers. To avoid interference between these, the carriers are spread in between by guard bands to distinguish different data streams with little to no overlap. So, let's say for radio broadcasting, this allows us to tune into different radio stations without static noise from other frequency channels. The second one is time division multiplexing, where different time slots are shared with the same frequency in digital signals. The more efficient type is the asynchronous TDM, where many signals are transmitted into different time slots according to specific timeframes for muxing in patterns that follows the correct data stream of different devices. So this prevents the telephone system from crashing when handling multiple voice calls over the same telephone line. And lastly is the wavelength division multiplexing, by transmitting optical signals of various wavelength over a signal fiber optic to boost the fiber's capacity for higher data rates than TDM with lower power consumption.
Thank you, Aidida. Next, I'll introduce you to the recent advancement of digital communication, which is 5G. So, what is it? So, 5G is the fifth generation of cellular network technology. It has faster speed, lower latency, and greater capacity compared to 4G. It's designed to connect everyone and everything virtually, including machines, objects, and devices. Here are some of the applications of 5G. First one, autonomous vehicle. 5G's low latency enables real-time communication between self-driving cars and infrastructure, ensuring a safe and efficient autonomous transportation. Next, remote surgery. 5G enables high-definition, low-latency video and data transmission, allowing surgeons to perform remote surgery with precision and accuracy. And lastly, we have industrial automation. 5G supports real-time control and monitoring of industrial equipment, resulting in faster and more efficient manufacturing processes. Next is the misconception of digital communication. The first one is privacy settings can keep my details safe online. Digital communication often involves sharing personal information, which can be vulnerable to data breaches and cyber attacks. This raises concern about privacy and security. Next, online interaction can replace face-to-face interaction. Over-reliance on digital communication can hinder the development of one's social skill, which could lead to social isolation and a decline in face-to-face interaction. And the last misconception is everything you see online is true. Digital platform can be used to generate and spread misinformation quickly and anonymously, which confuse and might harm some users.
To conclude everything that we've presented in this presentation, pulse modulation and multiplexing are key techniques in digital communication, enabling the efficient transmission and sharing of digital information. Pulse modulation ensures precise signal conversion, while multiplexing optimizes bandwidth usage by allowing multiple signals to share a single channel. Both are essential in today's fast evolving digital landscape, driving advancement in global connectivity and communication systems. However, as with any technology, they have their challenges, such as complexity, interference, and potential limitations. Therefore, proper implementation and management are crucial to ensure its effectiveness. That's all from us. Thank you for watching.